There are mysteries hidden, secrets waiting to be uncovered in the most ordinary objects, the things we take for granted each day. Consider a simple gold ring on your finger, a symbol of commitment and love, or the copper pipes in your home, silently carrying water through the walls. For centuries we sorted the world, categorized and classified, magnetic and not. A seemingly simple distinction. Iron, nickel, cobalt, magnetic superstars, the heavy hitters of the magnetic world. They cling to your fridge, holding up memories and reminders, power motors, driving countless machines and devices, guide compasses, pointing the way across vast oceans and unknown lands. Then there's gold, copper, aluminum, non-magnetic, or so we thought, a clear and distinct separation it seemed. We believed their inner lives were quiet, magnetically inert, holding no magnetic secrets, their atoms aligned in a peaceful, non-magnetic dance. But the universe hides profound truths in plain sight, often concealing complexity beneath a veneer of simplicity. Physicists dared to question the established order. If electrons are tiny magnets, the fundamental building blocks of magnetism, why do some materials seem magnetically silent? Where does all that potential magnetism go? Theories said their magnetic fields cancel out, perfectly balanced and neutralized, creating a perfect magnetic nothing, a void where magnetism should be. But what if there was a faint, organized signal, a whisper of magnetism just too quiet to hear? A subtle hum lost in the background noise. Our tools, overwhelmed by noise, the cacophony of the modern world, couldn't detect it. The signal remained hidden, masked by interference. So, we accepted the silence, mistaking the absence of evidence for evidence of absence, and built our understanding on it. A foundation built on an incomplete picture. But science advances by questioning the obvious, challenging assumptions, and pushing the boundaries of knowledge. Someone decided to listen more closely to the silence, to amplify the faintest whispers of the universe. The breakthrough wouldn't come from a giant accelerator, smashing particles together at incredible speeds, but from a new way of shining light on metal, a gentler, more revealing approach. The quest to find a magnetic ghost haunting physics for generations, a phantom presence just beyond our grasp. Sometimes the greatest frontiers, the most exciting discoveries, are right under our noses, hidden in plain sight, waiting to be noticed, waiting for a brighter light, a new perspective to reveal their secrets. And so the journey began, a quest to illuminate the unseen universe within. To find this elusive ghost, a magnetic whisper hidden within the heart of gold, scientists embarked on a quest. But to even begin to perceive such a subtle phenomenon, scientists needed a new kind of light, a tool precise and powerful enough to unveil the unseen, and that tool was a blue laser. Lasers, unlike ordinary light, are beams of organized light, a symphony of photons. Within a laser beam, their photons are not scattered and chaotic but marching in perfect lockstep, a unified front. For this quest, a journey into the quantum realm, a blue laser's high energy, its shorter wavelength, was absolutely key. It could interact with electrons in metal with pinpoint accuracy, without creating distracting thermal noise, the kind of heat that would obscure the delicate signal they sought. The blue laser became more than just a light source. It was a finely tuned probe, an instrument of unparalleled sensitivity. It was a key, meticulously crafted for a lock no one had ever opened before. This wasn't just shining a laser at metal, a simple act of illumination. It was something far more profound. It was inventing a new way of seeing, a revolutionary approach to probing the mysteries of matter. Enter the time-resolved magneto-optical Kerr effect, a mouthful I know, or TR-MOC for short. The core idea is to hit the metal with an incredibly short laser pulse, a fleeting burst of energy, then measure the reflection of that pulse, looking for a tiny twist in its polarization. This subtle twist, almost imperceptible, would reveal the presence of a hidden magnetic field. The entire setup required perfect harmony, a delicate balance of components, mirrors aligned with nanometer precision, lenses shaped to focus light with unwavering accuracy, detectors sensitive enough to catch the faintest glimmer, and laser pulses lasting mere femtoseconds, quadrillionths of a second. This incredible speed was essential to capture the electron's fleeting behavior. Before anything else, any other interaction could interfere and corrupt the measurement. In essence, what they were doing was remarkable. They built a camera, not for visible light but for magnetic fields, and with the fastest shutter in history. They were about to take the very first picture, a snapshot of the unseeable, of gold's hidden magnetic soul, a secret whispered only in the language of quantum mechanics. The blue laser was their flash, the source of illumination for this unprecedented photograph, ready to illuminate a secret kept hidden, a mystery unsolved for all of human history. The experiment was set, the stage was prepared, and the moment of truth had arrived. How does light find a magnetic field? Through the Kerr effect. Polarized light, when reflected from a magnetic surface, twists ever so slightly. For iron, this twist is obvious. For copper or aluminum, it was thought to be zero. The challenge: detect a twist almost infinitely small. Imagine a stone skipping across a lake, nudged by an invisible whirlpool, subtle but detectable with the right tools. The laser pulses the stone, the metal, the lake, the hidden magnetism, the whirlpool, the experiment. A pump pulse jolts the metal, aligning any hidden magnetic domains. A weaker probe pulse follows, measuring the twist. By varying the delay, scientists watch the magnetic signal appear and fade. Like striking a bell and listening to its ring, they separate signal from noise. Repeating the experiment millions of times, the random noise cancels out. At last, the faint magnetic whisper emerges. The day of the experiment arrived, filled with anticipation and meticulous preparation. Every detail had been checked and rechecked, ensuring that the conditions were perfect for this groundbreaking investigation. The team knew that the slightest imperfection could compromise the results. A sample of gold, long considered non-magnetic, an inert element in the realm of magnetism, was carefully placed in the heart of the scientific chamber. This seemingly ordinary piece of metal held the potential to rewrite textbooks. The blue laser fired, a precisely calibrated pump of energy, initiating the experiment. Then the probe meticulously scanned the sample, searching for any sign of a magnetic response. At first, the data was just noise, a flat line, a chaotic jumble of meaningless fluctuations. It seemed as though the gold was living up to its non-magnetic reputation. But the team persisted, driven by their hypothesis. They employed sophisticated algorithms, averaging millions of measurements to filter out the background interference. Slowly, painstakingly, a curve emerged, a subtle deviation from the flat line. It was a signal appearing after the pump, a fleeting magnetic response, then decaying back into the noise. They had struck the bell of gold and for the first time in history, heard its faint, almost imperceptible ring. The signal was weak, thousands of times fainter than the robust magnetism of iron, a mere whisper in comparison. But despite its faintness, it was undeniably real, a genuine magnetic signature emanating from the gold. And remarkably, it matched the theoretical predictions exactly. A magnetic ghost, predicted by advanced physics, finally revealed in the laboratory. To confirm their findings, they repeated the test with copper, and then with aluminum, each metal meticulously prepared and analyzed. Each metal revealed the same faint magnetic echo, confirming that this wasn't an anomaly, but a fundamental property. These metals weren't silent in the magnetic realm, just incredibly quiet, their voices too soft for our previous instruments to detect. Our old tools, designed for stronger signals, were simply deaf to their subtle whispers, unable to perceive the faint magnetic fields. This groundbreaking discovery erased the neat black and white line between magnetic and non-magnetic materials, blurring the boundaries of our understanding. The world, it turns out, is far more subtle and interconnected than we had previously imagined, with hidden properties waiting to be uncovered. The chapter on magnetism, a cornerstone of physics, had to be rewritten to incorporate this new reality. The universe, in its vastness and complexity, had kept this secret of subtle magnetism hidden for billions of years, waiting for us to develop the technology to unveil it. Now, with our advanced tools and techniques, we could finally hear the universe's faint magnetic song. The silence we had perceived was merely an illusion, a limitation of our own perception. The magnetic ghost, once a theoretical concept, was undeniably real, a testament to the power of scientific inquiry. This wasn't just a new property, it solved a century-old puzzle: Larmor diamagnetism. In 1900, Sir Joseph Larmor predicted that all materials, even non-magnetic ones, should create a tiny opposing magnetic field when placed in a magnetic field. The math was solid, but no one could directly observe it in metals. It was too weak, too fleeting. The blue laser experiment finally captured it. The pump pulse nudged the electrons. The probe measured their faint opposing field. The decaying curve on the screen was the first direct observation of Larmor diamagnetism in a metal. A theory, dormant for a century, was finally proven. Science is a relay. One generation plants the seed, another brings it to light. This discovery didn't just add knowledge, it confirmed the foundations of physics. The riddle was solved. The ghost was seen. The music of Larmor's score was finally heard. To grasp this discovery, imagine an alien in a silent library, thinking humans lack music. Then, with headphones, the alien hears a symphony. Music was always there, just unheard. Our old tools only heard the loudest magnetic sounds. Iron's heavy metal concert. Gold, copper, and aluminum were the silent library. The blue laser is our new set of headphones. It reveals a spectrum of magnetic behavior, a hidden symphony in every material. Iron is the booming drum, gold a faint violin. Magnetism is universal, not rare. The laser lets us briefly conduct the orchestra, bringing order to the chaos. For a fleeting moment, we hear the music. The copper wire in your wall, the aluminum foil in your kitchen. They all have a hidden magnetic life. The world is layered with secrets, waiting for new tools to reveal them. We've just learned to listen to the symphony of the cosmos. This discovery is more than a curiosity. It opens new frontiers in physics and technology. Now we can study the magnetic behavior of materials used in superconductors and quantum computers. The technique could revolutionize data storage. Imagine writing and reading data with pulses of light, not just electricity. This paves the way for spintronics and photonics, faster, more efficient devices. We can now design materials with tailored magnetic responses, creating ultra-sensitive sensors or quantum components. Understanding hidden magnetism lets us become architects of matter, not just users. The most exciting implications are those we can't yet imagine. Every new tool has reshaped civilization in ways no one predicted. We've gained a new sense, the ability to see ultra-fast, ultra-weak magnetism. The universe just got bigger, and so did our questions. This journey began with a simple question about magnets. It led to a century-old theory and ended with a blue laser revealing hidden truths. The story is a testament to the scientific method. Question, invent, observe. It reminds us the world is richer than we think. This breakthrough inspires us all. There are still fundamental discoveries to be made, even in the ordinary. The next leap may come from a small lab, not a billion-dollar project. The materials of the future may have properties we're only beginning to uncover. By learning to see and manipulate hidden magnetism, we gain a powerful new tool. The universe guards its secrets, waiting for us to ask the right questions. Each discovery peels back another layer of reality. The future is something we build, one pulse of light at a time. Our exploration is twofold, outward to the stars, inward to the atom. The discovery of weak magnetism is a landmark on that inward journey. It bridges quantum theory and everyday metals, a puzzle piece clicking into place. With every discovery, our island of knowledge grows and so does its coastline. Each answer births new questions. Can we amplify this effect, control it with light? The journey never ends. This story is about the human spirit, our drive to know what's never been known. The quest for knowledge is our noblest adventure. The next time you see a copper pipe or gold ring, remember, it hums with a faint cosmic energy. The universe is full of unseen wonders, waiting to be discovered. We have only just begun our journey to the known.